Hi, I'm starting chapter 6. Chapter 6 is on number theory and the real number system. And the first section is on number theory. So I'm going to start with one definition on divisibility. So that's on page 238. If A and B are natural numbers, we say that A divides B, written A bar B. So this stands for A divides B. Provided that there's a natural number Q such that B equals Q times A. Other ways of stating this is that A is a divisor of B, A is a factor of B, or B is a multiple of A. A way to testing to see if A divides B is to actually divide B by A and see if you get a zero remainder. Okay, for example, we can say that 7 divides 35. So I'm going to write like this, that 7 divides 35 because there's a number and you know that the number is 5 that multiplied by 7 is equal to 35. So 7 divides 35 because 7 times 5 is equal to 35. Or and 11 divides 11 because there's a number, in this case 1, that multiplied by 11 is equal to 11. Okay, with this in mind, I'll give you the definition of a prime number. Okay, so I'm trying to copy this definition. On page 239. A natural number greater than 1 that has only itself and 1 as factors is called a prime number. A natural number greater than 1 that is not prime is called composite. So the first note is that 1 is not a prime number. The smallest prime number is 2. So some examples of prime numbers are 3 is a prime number, 5 is a prime number, 7 is a prime number, 11 and 19, or I could keep on going. But these are examples of prime numbers. They are not the only ones. 3, 7, 11, 19, and 37 are prime numbers. Their only divisors are 1 and themselves. And on the other hand, 42 and 88 are composite numbers. they have divisors other than 42 and 88. Like 42, you could write this as 6 times 7. But that's not the only way. That could also be 2 times 21 or 3 times 14. At the end, if you write this as a product of prime numbers, that's 2 times 3 times 7. And 88, it has divisors other than 1 and 88. Okay, so one way to write this is 8 times 11. So 8 and 11 are divisors, or any combination. So if we write 8 as a product of prime numbers, that's going to be 2 times 2 times 2 times 11. And from there, we can get something like 4 times 22 or 2 times 44. So those are a few possibilities. Okay, so one well-known way to generate a list of primes is called the sieve of Eratosthenes. Let's write this down. And the best way to illustrate this is with an example. I cannot think of a clear way to define it. So I'll show you I'm going to do the example in the book to show you how this works. This is also on page 239. Okay, we're going to use the sieve of Eratosthenes to find all prime numbers less than 50. Okay, so what we're going to do first is write every natural number up to 50. So we're going to make a list of all natural numbers up to 50. Okay, I have 20 more. And last 10. Okay, so the way this works is by crossing numbers that are not prime numbers. So 1 is not a prime number. The smallest prime number is 2. So 2 is a prime number. If 2 is a prime number, every multiple of 2 is not going to be a prime number. So we can cross every multiple of 2, and with that, we're going to get rid of half the numbers in this list. So we cross every multiple of 2 because those cannot be primes. So that eliminates half of the numbers we had in the list. Okay, so 3 is a prime number. So every multiple of 3 that we have not crossed yet is not a prime number. That means 6 is not prime. We already crossed that, but 9, 15, 21, 27, 33, 39, and 45 are not prime numbers. The next prime number is 5. So we're going to cross the multiples of 5 that we haven't crossed yet. The next one is 7. So we crossed almost every multiple of 7 except 49. And from there, 11 is prime. So we already crossed 33. Well, we already crossed 22, 33, and 44. 13 is prime, and we already eliminated 26 and 39. 17 is prime. We already eliminated 34. 19 is prime, and we already eliminated 38, the only multiple of 19. And so forth. 23, or we already eliminated 46. So the last prime numbers are going to be, so we're going to circle the remaining prime numbers. Okay, so the prime numbers less than 50. So now I'm going to write those as a list. The prime numbers less than 50 are 2, 3, 5, 7, 11, 13, 17, 19, we got 23, 29, 31, 37, 41, 43, and 47. So those are the prime numbers less than 50. So I'm going to read the next paragraph in the book. You can also use technology. Now, if you wish to find all primes between 1 and 1,000, well, using the sieve operator dozens could take a lot of work. You may want to use technology. I will show to the left. However, technology can make mistakes. The list of primes shown is not correct. So, yeah, they have this calculator that supposedly generated a bunch of prime numbers, but there's going to be one missing. 89. Well, that's the first I found. 89 is not 89 is a prime number, and it's not in this list. So 89 is missing. Okay, it's time to talk about divisibility. So I'm going to read this table. So in checking larger numbers for primality, it is useful to have some quick tests for divisibility so that we don't actually have to do a lengthy division. For example, it would be nice to be able to look at the number 21,021 and have a quick test to see whether 3 divides into it without actually having to do the division. So the table 6.1 on the next page lists some divisibility tests. We will examine why these tests work in the exercises. Although there are divisibility tests for 7 and also 11, they are hard to remember, and you are really better off simply dividing by 7 rather than using the test. So I'm just going to read the divisibility test. I'm going to zoom out just a little bit. Okay, so a number is divisible by 2 if the last digit of the number is divisible by 2. In other words, if the number is an even number. A number is divisible by 3 if the sum of the digits is divisible by 3. Like the one we mentioned, 21,021 is divisible by 3 because the sum of the digits is 6, which is divisible by 3. A number is divisible by 4 if the number formed by the last 2 digits is divisible by 4, or if it is a double zero. Like 102,736 is divisible by 4 because the last 2 digits 36 are divisible by 4. A number is divisible by 5 if the last digit is either 0 or 5. A number is divisible by 6 if the number is divisible by both 2 and 3. A number is divisible by 8 if the number formed by the last 3 digits is either a triple zero, is 3 zeros, or it is a number divisible by 8. Number 9 is very similar to number 3. A number is divisible by 9 if the sum of the digits is divisible by 9. Like 2,081,763 is divisible by 5 because the sum of the digits is 27, and 27 is divisible by 9. And probably the easiest one, a number is divisible by 10 if the number ends in 0. Okay, so I'm going to, let's see, I'm going to do one example similar to number 3. We're going to use the divisibility tests. Okay, we're going to test the number 12,288 for divisibility by each of these numbers by for divisibility by 2, 3, 4, 5, 6, 8, 9, and 10. Okay, so let's start with A. Okay, so this number is divisible by 2. So this is divisible by 2 because the last digit is 8. It is also divisible by 3 because the sum of the digits is a number that is divisible by 3. So if we add digits, that's 21. So yes, it is divisible by 3. Because 21 is divisible by 3. It is also divisible by 4 because 88 is divisible by 4. This one is not divisible by 5 because the last digit is not 0 or 5. Okay, and we already saw that it is divisible by 2 and 3, so it must be divisible by 6. Because it is already divisible by 2 and 3. It is going to be divisible by 8. 288 over 8 is 46. So I'm not going to do the division, but 288 divided by 8 is 46. So this number is divisible by 8. is not divisible by 9 because 21 is not divisible by 9. So it is divisible by 3, but not by 9. Okay, because the sum of the digits is not a multiple of 9. And it is not divisible by 10. If it's not divisible by 5, it cannot be divisible by 10. Okay, so one tip is that to test a number, or to find the divisors, to test a number for divisibility, take, let's see, to test a number A for divisibility, take the square root of A. And check whether it is divisible by each integer less than the square root of A. Okay, so I'm just going to write like this, whether it is divisible by the square root of A. Okay, for example, we're going to use that to find all the divisors of 91. Okay, so rather than using the divisibility test one by one, we can take the square root of 91, which is approximately 9.54. And we are going to test the number for divisibility by every integer or every prime number, not every prime number, every integer between 2 and 9. So test for divisibility by 2, 3, 4, 5, 6, 7, 8, and 9. Because 9.54, that was, okay, we have that the square root of 89 is 9.54. So the greatest integer less than 9.54 is 9. So I'm just going to cross that. The last digit is 91, so it's not divisible by 2. 9 plus 1 is 10, so it's not divisible by 3. And if it's not divisible by 3, it cannot be divisible by 9. And by the way, if it's not divisible by 2, it cannot be divisible by 4, 6, or 8. And the last digit of 91 is 1, so it cannot be divisible by 5. All we have left is 7. We are going to test for divisibility by 7. But 91 divided by 7 is 13. Okay, so the divisors of 91 are 1, 7, 13, and 91. And we're going to do the same for 347. Final divisors of 37, or determine that 347 is a prime number. So let's start by taking the square root of 347. On a calculator, that's approximately 18.6. So we're going to test for divisibility by every integer between 2 and 18. Okay, so we're going to test for divisibility by 2, 3, 4, 5, 6, up to 18. Okay, the last digit is 2. 347 cannot be divisible by 2. And if it's not divisible by 2, it cannot be divisible by either 4, 6, 8, 10, 12, 14, 16, or 18. Then the sum of the digits is 14. So it cannot be divisible by 3. And if it's not divisible by 3, it cannot be divisible by 9 or 15. The last digit is 7, so it cannot be divisible by 5. By 5, well, and we already eliminated 10 or 15. So we only have left 7, 11, 13, and 17. So all we have left is this one. Okay, so check for divisibility by 7, 11, 13, and 17. But 347 divided by 7, I'm just going to do those manually. Well, I'm going to do those on the calculator. So let me share this. So 347 divided by 7. Well, we don't have an integer. 347 divided by 11. Still, we don't have any integer. 347 divided by 13. Okay, so 347 so far is not divisible by 7, 11, 13, and 17. And the last try is 347. Check whether it's divisible by 17, and it is not. Okay, so 347 is not divisible by any of this. And its only divisors or I shouldn't even write that. So it's not divisible by any of this. Therefore, it is a prime number. Its only divisors are going to be 1 and 347. And the last thing I'm going to do is prime number decomposition. So I'm going to mention the fundamental theorem of algebra. The fundamental theorem of arithmetic. The fundamental theorem of arithmetic says that every natural number greater than 1 is a unique product of prime numbers, except possibly for the order of the factors. So product could mean a single prime number. This is page 242. Okay, so we are going to factor 8,190 as a product of primes. And we can use a factoring tree. Okay, so 8,190. Okay, we're going to write a factoring tree. So this is a number that ends at 0, and it is divisible by 10. So we have 819 times 10. And 10 can be factored as 2 times 5. So we have factors at the primes at the end. If we have primes at the end, we're going to stop the factorization there. 819, the sum of the digits is 18, so that's divisible by 9. And that's going to be 91. So that's 91 and 9. We learned that 91 is 7 times 13. And 9 is 3 times 3. Okay, so the numbers at the end of the branches are all primes. And 8,190 as a product of primes. The factorization is unique. We're going to write this in order. That's 2 times 3 times 3 times 5 times 7 times 13. Okay, so this is only the first part of section 6.1. I will finish the section in the next video. Thank you for listening.